if you remember the table yesterday, diffusion pump is actually a kind of kinetic pump. Okay, it's a kinetic pump. So there is transfer of gas, okay, with the help of some kinetic energy, and this is what we are going to understand now. Okay? So just write down few points before we proceed. Okay, the first thing is it's a kinetic pump, okay, and it definitely produces a better vacuum. Okay, it produces higher vacuum. Okay, in comparison to rotary or root pump. Okay, so whatever pump we have seen till now, compared to both of them, it will definitely give you better vacuum. These pumps are also application dependent. What exactly is the application? If you don't need a higher vacuum, you don't really consider option for that. Okay? So that is there. And then what happens usually is whatever gas molecules are there which you need to take out, okay, we will actually impart some kinetic energy, or in other words, we can say we can actually impart some momentum, okay, into them, so that it can be actually taken out. Okay, so this is what is done with the gas, and that is why it is called a kinetic pump. Okay, and this basically, after imparting this momentum, as I said, this momentum is used. Okay, basically its energy is used. Well, yes. So basically for creating a vacuum, we should not have any gas molecules. So even if you have air which needs to be taken out, these are nothing but gas molecules, and this is what is done in case of a diffusion pump. So before we proceed on how exactly is the working principle, right? What we'll do is we'll just try to draw our image, okay, and then try to understand that. Okay. Once the image is clear to you, I think the writing part should not be very difficult. So let's just draw one picture here for our diffusion pump. So this drawing should not be very difficult, but yesterday, as I've showed you just some images, so sometimes it becomes a bit difficult to remember those images. Okay, so I'd rather suggest you to just practice it once or twice. Okay, so today at least I can draw the image, so I think you can actually have an approximate idea of how to draw it. So this is more or less symmetrical. Okay. Okay, so what happens is this: you basically have got a chimney kind of structure, okay, and this is basically your vacuum space. Okay, so what do I mean by this? Actually, this is the region which needs to be evacuated. Okay, so along this, the evacuation chamber is basically connected. Okay, so here the evacuation chamber is connected. Okay, we have it here, which needs to be evacuated, and there will be generation of heat. So there are some cooling coils which are there, and then these cooling coils you can just draw in circles and put it on all sides. Okay, so this is nothing but cooling coils. So we can just write it down. Okay, cooling coils, and of course there needs to be an outlet as well. Okay, so I have to just this part. Okay, and we will just draw one structure here. So everything is more or less connected with cooling coils. Okay, and this is nothing but to the pump. So whatever has been given taken out needs to be expelled. Okay, and that can be done through the pump. Okay, and this is basically the chimney. So this is your chimney. Okay. And what happens is that if there is a vacuum space which you need to create a vacuum, this air from this vacuum will actually come rushing down. Okay, so it will go along this direction and it will finally be expelled. Okay, it will finally be expelled. So how does it expel? This is something which we are going to look into. Here we basically can consider this part. Okay, this is nothing but a heater. You can actually go to a very high temperature. We have got some oil inside, okay, and if we heat that, those oil will actually start to go up, rise up. Okay, and they will try to rush out of these chimney holes. Okay, and as they rush out, whatever air is there in the surrounding, it will take that air with it and then try to expel it out of the chimney. Okay, and this is how a diffusion pump usually works. So what we are going to do is we are probably going to write down some important points on this. Okay, once we write down, I think it will be more clear to you. Okay, so let's just keep this image in mind and try to write down few points. Okay, so maybe I can say it's a construction part. Okay, so maybe we can write it down as construction. So number one, we basically have a chamber. So we have the image by the side, so I think we can actually relate it easily. Chamber housing, you can say, okay, having uh, oil vessel with heater. Okay, so I think it's obvious here. This is the chamber housing, which is having some oil in it. Okay, so we're talking about the part where this there. Okay, and on top of this chamber we have the chimney. So we have the chimney, and third we do have the nozzle. Okay, through which the expelled gas will fizz out. Okay, and then we have got the cooling coils. Okay, so cooling coils, I think it's quite obvious. If you're heating it down upright, we need to also cool it down at the surface where it's not needed. The heat is not needed. So cooling coils carrying water. So water is actually a good coolant, okay, in this particular case. And this basically is effective, okay, effective when coupled with backing pump. So it's not that you can just use this. You need to use a backing pump along with it. Okay. And one more important thing is it cannot be operated because you are going to evacuate a chamber. That means you are going to have a vacuum where the pressure is much lower than the atmospheric pressure. Okay. So what happens is it cannot be operated at atmospheric pressure. Okay, cannot operate it at atmospheric pressure. Okay, and hence operated at molecular region. At molecular region. So you uh, already have taken out a substantial amount of air out of the system, okay, and it is operating it in the molecular region. Okay, so first roughing needs to be done. So this is important. First the roughing is done and then only you can actually use it in the molecular region. So this is how this basically the construction part is this for this diffusion pump. Okay, so what we're going to do now is we are going to just look into the working. Okay, and I think for working we may maybe copy the image. Okay, so we can have it by side. So the working is simple. I think you have already got a brief idea about it. Okay, and let's try to just write down some parts here. Okay, so let's try to talk about the working. So what happens is the heater which we actually have, okay, vaporizes, okay, vaporizes the oil, and these hot vapor. So when we vaporize it, it will actually rise, right? This hot vapor will rise, okay, into the vapor chimney. So the image can be clearly seen, okay. The vapor will actually rise into the chimney. So I'm talking about this part right now, okay. It's basically slowly rising, okay. And what happens after that? This hot vapors are deflected. So it has got a surface and it gets deflected from there, and then it will actually try to take a path which is less resistive. So it will go out through this nozzle. Okay. So the hot vapors are deflected downwards. Okay, by nozzle. So we have the nozzle which actually deflects it. Okay, and then as soon as it gets deflected, this actually will move out at a very fast speed. Okay, so this we can say jet of hot vapor, of hot vapors. Okay, move downwards, move downwards at supersonic speed. So I think this is logical, right? It will move at a very fast speed because it is already vaporized state, so it will actually have a large energy. Okay, and this supersonic speed will basically impart a momentum. Okay, and imparts a momentum. Okay, to randomly moving gas molecules. So the gas molecules are already there because it is connected to the chamber which needs to be evacuated. So you have the gas molecules here, okay, and it is rushing downwards, and along with it, it will actually carry the gas molecules with it. Okay, so randomly moving gas molecules in the chamber. So this is the first part. Okay, this is simple. Okay. And what happens is this momentum will be enough to actually deflect it towards the pump outlet. Okay, so it will deflect, okay, deflects the molecules towards the pump outlet, towards the pump outlet. This is what is happening here. Okay, and we use a backing pump. Okay, so the pump outlet is also connected to a backing pump because whatever is there, it needs to be removed. Okay, is constantly, it's not that the chamber will be evacuated at one go. It's happening in cycles. Okay, each cycle a backing pump is used to constantly remove. Okay, so a backing pump is constantly removing, we can say, the gas molecule. So what happens after that is you're basically going to just take it out, expel the gas molecule, and then finally you're going to get a vacuum. Okay, so sometimes it does happen that the hot oil that we have here, okay, condenses. Sometimes, not sometimes, always it will happen because I don't want to take out the oil out of the system. I just want to have the gas out of the system. Okay, so what happens is these chambers, these cooling coils will actually condense the oil and make it settle back into the chamber, okay, which will be again heated, and then the process will keep on continuing. Okay, condenses on cold wall, so you're not changing the oil every time. Okay, and returns to the vessel, uh, vessel at the bottom. Okay, so this image is just a representation. This might not be a perfect image. Okay, so we may be having the heater in this connected in such a way so that only this part is heated. Okay, and then as soon as the oil gets condensed, it will actually come, and the mechanics is such that it will get accumulated in this particular region, and then it will again start heating, and the same process will follow. Okay, so this image is just a representation, not a perfect image. Okay, So don't get confused here. But there is a common problem, okay? But there. So what is that common problem? The common problem is backstreaming of oil. Backstreaming of oil, which causes contamination. So what does it mean? It means that if this is not properly connected with the vacuum chamber, is if there is any kind of gap in between, the chances are that this oil might go back into the chamber which needs to be vacuumed. Okay, so we don't want that. Okay, that is basically nothing but contamination that will happen. Okay, so this needs to be avoided. Okay, so uh, how we do that, that is actually one of the major role of the cold trap that we are using. Okay, so what we have is a cold trap. Okay, is used to prevent flow of oil oil molecule into the vacuum chamber. So this cold trap is used. So the thing is, as soon as the oil comes out of this chimney region, the cold trap is there. It will impart the energy to the gas molecules, and this will actually come fizzing out. And the cold trap will condense the gas or the molecule immediately, or the oil immediately, and this will actually settle down fast. Okay, if the cold traps are not used, the chances are that this oil might go into this particular part of the vacuum chamber also. Okay, so that's why it depends on this. Okay, so this pressure will basically depend. Okay, this pressure that we are talking about. Okay, the lowering of the pressure inside the vacuum chamber. Okay, will depend on a certain factor. So the first one might be vapor pressure of oil. Vapor pressure of oil. So oil plays a very important role. So that's why the vapor pressure is important. Okay, of course, pump design. So as I said, the design is important. Which part is heated? Okay, how the oil is flowing back into the region where the heating will again work. Okay, and so on. So pump design, it depends on that. Okay, and based on this, the price of these kind of vacuum pump also will change. Okay, and of course, what is the gas load? Gas load from vacuum space. So if the vacuum space is loaded too much with gas, probably this won't work. Okay, so the first roughing is done, and then only it can be done. It's a gas load from the vacuum space. It also depends on this. Okay. Okay. Now what I'm going to do is we're going to see that how this roughing pump is used along with the other pumps that we have actually studied. Okay, so I'm just going to draw a figure, and then probably it will be a bit more clear. Okay, and this is actually important because I told you that I can use a turbomolecular pump or this diffusion pump that we are talking about, but before that we do need to do the roughing. So if I have a chamber where I actually need to do the roughing, how exactly is it connected in connection in along with the roughing pump? Okay, the diffusion pump, the roughing pump, how they are connected. So this is something which we are going to draw now. Okay, so let me just draw this. Okay, so let's say this is your chamber that you need to vacuum. Okay, so this is your vacuum chamber. And then of course it does not, it's not that simple as it looks. It's just a block diagram. Okay, but if you're doing any kind of work on experimental techniques, okay, where you're using pumps and all, these ideas should be more or less okay. Okay, you should be able to grasp it easily. So this is basically a typical block diagram, you can say. Okay. Such designs has a very important part which we usually call as valves. Okay, So valves are something like diodes that we actually study in electronics, or vice versa. Sometimes when we study electronic and study diodes, we say that physically a valve is nothing but like a diode. So a valve is something which will allow the flow of, let's say, air in this case, or the gas molecules in this case, okay, only in one particular direction. Okay, so this is important. So depending on how precise the system should be, a design might be even more complicated. Okay, but right now we are just concentrating on this simple diagram. Okay. They are usually sealed. Okay, and it's not like uh, these are machine-made devices. Okay, so you have a valve here. Okay, so this is a valve. Okay, this also will be a valve. Okay, maybe I can just put a cross here. Okay, let's symbolize this as a valve. This might also be considered as a valve here. Okay, and then maybe I can just write down what are the different parts here. Okay, so this is basically a vacuum chamber. So this is something which we need to vacuum. Okay, we need to take the air out of it. Okay, and then we have the diffusion pump. So diffusion pump will be this diffusion pump. These are nothing but, we basically, let's call this as a roughing valve, because it is connected to the roughing pump. Okay, roughing valve. So you remember roughing valve or roughing pump is nothing but the rotary pump that we had studied in the first part of understanding the different kinds of pumps. Okay, this is basically called a vacuum backing pump. And both roughing and backing, okay, are there. Okay, so this will actually give a backup to this diffusion pump, so this is called backing pump. The chamber is roughed before, a rough vacuum is created in the chamber before connecting into the diffusion pump, so we call it as the roughing valve. Okay, and then finally we have got the rotary pump. So the rotary pump is this block is basically representing the rotary pump. Okay, so this is what is there now right now. Okay, so this is what we have to see here. Okay, it's very simple. And I will just write down some sentences. I think then it will be a bit more clear to you, but its idea is simple here. We don't open all the valves at a time. Okay, so one valve is opened at a time. Okay, so the first point is one valve is open at a time. So at a time there is only one valve which is kept open. So let's say I will open the roughing first. Okay, so the roughing valve. Okay, so what we will do is we will open the roughing, so it is open, and then backing is closed. Backing, let's write it down in point wise, okay, so that you may remember it clearly. But you can always write down sentences for this. Please try to make sentences out of it. So you see this roughing is open, so that means this is open now, and this is closed. The backing is closed. So what does it mean? That whatever we have here, okay, whatever air molecule we have here has no chance of moving along this direction because this is closed. So this is open now. Okay, so at the first stage this is open. So as soon as this is open, the air will start rushing in. Okay, and then this will actually be in flow following this path. Okay, this is going to follow this particular path. This is the first step that happens here. Okay, so we have kept it closed, we have kept this open, and the vacuum chamber is both connected with diffusion pump and rotary pump at the same time, but then one of the pump is open and the other pump is closed. Okay, and this is how it works. Okay, And how does it work? It is basically used to create a, okay, maybe we can write it here, okay, to create a rough vacuum, right? So create a rough vacuum. And this, if any typical device, okay, depends on how much space you are going to vacuum, but then this is actually run to about 1 to 2 hours, okay. In the next stage, what happens is roughing is closed now. Roughing, quite obvious because you have already roughed it out, okay. Roughing is closed, okay, and backing is open. So in the next stage, what happens is this will basically be closed, okay. So this is closed now, number one, and then this will be open, okay. So what happens is that you've already taken substantial amount of gas molecule out of the chamber. Now the diffusion pump can work, okay, and it will actually drag out the remaining air out of the system. When the remaining air is taken out, this needs to be expelled from the diffusion pump, and that's why the backing is open. So rotary pump plays a role both before high vacuum is created and also during the process when high vacuum is created. Okay, so both the cases it's important. So this block diagram gives a very clear picture. Okay, so backing is opened, and why I'm saying this, I hope you understand this. Okay, I'll tell you. Just go back to the previous image to explain this. To operate diffusion pump, sorry, in molecular region. Okay, so this is what is done. So how they are used together, this is the block diagram. Okay, why I'm saying this, because I've already explained this here. See, this is written to pump. So you might be thinking about what kind of pump I'm talking about here. Okay, so first I say that I use a rotary pump to do a rough vacuum, and then again I say that this turbo or the diffusion pump is actually connected to the same rotary pump. How it is connected 2 times, okay, and that is why I have drawn this block diagram to make this clear. First, this is operated, roughing is done, and then this is closed. This air is actually coming into the diffusion pump now, and from the diffusion pump we again need to expel the air, and that is why we are basically using the backing pump. Okay, so that is there. Okay, and I think I should not write down backing pump here. This is not backing pump, sorry, this is backing valve. Okay, so both the rotary pump acts both as a backing valve, okay, as a backing pump as well as a roughing pump. Okay, this is what is the logic behind. So this might be an objective question to draw a approximate block diagram of a vacuum chamber which is connected to both diffusion pump and rotary pump, and probably just 2 marks for this. Okay, if we just draw the block diagram, explanation should not take much of time. Simple. Okay.